these two memory locations that actually hold addresses of the status register, which is FE00, and the data register is FE02. And the other thing that we kind of want to do with this thing is we're going to read in a value and store it here. We needed this thing to strip off the ASCII coding, which is a 3-0 hex, and that turns out we want it negative, so we have FFD0. Okay, now, I may not end up with the same registers I had last time. We won't worry too much about that. We're going to begin here by, we've got a wait loop where we basically check what's in that status register, and usually the easiest way to do that is to load a register except that we're going to load indirect so that we don't load this thing. We use this thing as an address to find what's actually out there. And we wait until the contents of that status register is negative, which says that there's a character ready for us. Then we can load indirect register 0 from the data register. Now then, the way we were doing it, we did a check to see if this thing was a carriage return, an enter key, which we did by getting the ASCII value for the carriage return, which was a 12 hex. I think we did carriage return is a 12, 13. 10 is a line feed. Number 13. And we want to subtract that from this to see if they're equal, so we do a not. And then an add. And then we'll copy this character here. So this gives us in register 1 the difference, and we'll say branch of 0 to done. Otherwise, what we have in there is a legitimate digit, and so we'll strip the ASCII code off, which we do by saying load register 1 from ASCII. Add, no, I want register 0 here. Now I have to accumulate that digit onto my sum, which we'll do up here. Register 3. We'll clear register 3. And so now down here I want to multiply register 3 by 10. This is kind of about where we stopped last time. We've got our routine in here to check, see if we're done. If we just comment on this whole thing, this is a check to see if carriage return was entered. That means we're done. This is to strip the ASCII code. And so now I multiply this thing by 10. I do that by saying I add register 3 to itself. That gives me 2 times the value that's in there. Register 4 now contains 4 times what was in there.
But there's just 0 in register 3, isn't there?
Yes, but that's going to change. But I have to write my loop as though I were in the thing. Yeah, initially there's a 0, but we're going to trace this thing here in just a moment. This now gives me 8, which I will add. Okay, the net result here is to multiply register 3 by 10. Now my digit that I just got in is in register 0, so we will add that on, and now we will do an unconditional branch back up to weight. Now, in terms of a complete program to get this thing in here, why that done, really about all we're going to do here is store register 3 into X and then halt. Okay. Now let's trace this thing through and watch and see, again, remind you why we're doing this down here. Let's see, we're going to work with register 0, register 1, and register 3, and let's see, we do have register 4 down there, don't we? Okay. For the sake of discussion, without getting too far into things, we will enter a 3-digit number. 763. Now let's see what that is going to end up being in terms of hexadecimal. We'll work through this thing in hex. 64. Okay, so that should end up being a 2FB in hex. Let's see if we can get it following through here. Okay, we know what this thing does. that gets us a 0 in here. Okay, we won't fuss through this thing too much. That just waits until you press the first key out there on the keyboard. The thing that gets loaded into register 0 here is the ASCII code for the first digit that I enter, namely 7. Okay, so in hex, that's a 3-7. Okay, you can check the ASCII table at the back of the book. That's what we get out of it. Okay, I load register 1 with a 0, 0, 1, 3. We do a naught on that, which gives us an FFED. Well, actually gives us FFEC. Now let's go through all the steps. It gives us a C. And then we add 1, which gives us FFED. Okay, that's at this point. Now we add that to register 0. 0, 0, 3, 7. 13 and 7 is 20, that's 1, 4. 15 and 3 is 18, that's 1 times 6 plus 2, 0, 0. Doesn't really matter what the result is, it's not 0. So I do not take this branch, I come down to here. So now I scrub out that result and replace it by this FFD0. Yeah, I keep using register 1 over and over again for different functions, but as soon as I'm through with something, I can go ahead and do it. Now I'll add that on to what's in register 0. I get 7, 13 and 3 is 16, 0 carry 1, 1, 0, and the last carry is lost. Okay, see, I stripped off the ASCII code. I now have exactly that first digit that I put in there. Now I add register 3 to itself. That still gives me a 0. I add it to itself again and put it in register 4. Add register 4 to itself, add it back. Exactly as someone pointed out, I'm left with 0. Because 10 times 0 is 0. But now I add register 0 onto that, and so now I end up with 0007. Now I do my unconditional branch back up to here and wait until the next key gets pressed. When it does, I said it was a 6, so once I come out of this loop, there is a code out there at the data register. It gets loaded into register 0. It's 0036. Those are gone. Okay, I'm not going to go through this again, but again, I'll do the same thing. I load this up, I toggle the bits, I add 1, and then I add the 3, 6 onto it. The only difference is that now I'm going to get a 2, 3. But in any event, it's certainly not 0. So here I am here again. I load register 1 from this ASCII location, which is FFD0. Add that on to register 1. FFD0, 6, 13 and 3 is 16, 1, 1, and the 1 gets lost, and there's my 6. Okay. Okay, so now I've got my digits. Now we go through this process. Now this time it's going to be different. Because when I shift this one place, I get 14. Now I shift it again. If you want to look at it. See, we have this in there with a bunch of zeros. When I shifted it one place, I got this, which is 14. I shift it again, and I get 1 C. $16 and 12 is 28. 2 times 14. Okay. Let's see. That one goes into register 4, not into register 3. That's this instruction right here. Now I get 001C there. Now I shift register 4 again. I get 111000. That's 3 times 16 plus 8. 48 and 8 is 56. Sure enough, that's 2 times 28. So now I get 0038. Which I now add back onto register 3. 0038. 8 and 14 is 22. That's 1 times 16 plus 6. 3 and 1 is 4. Okay, just to check where we are, what is 4/6 hex in decimal? Well, it's 4 times 16, which is 64, plus 6, 70. 10 times 7. Okay, so I have multiplied now by 10. Now I add what's in register 0 onto that. And I get 004C. Adding 6 onto this gives me 76. If I were to stop at this point, that's exactly what I have entered. Okay. Watch the thing through then to the end. We now have this unconditional branch. We go back up here. We wait until the next key is entered. 3, I said. The hex code that comes in there is 33. Again, we go through this process of adding that number into there, and we still don't get 0. So we don't branch. We add the decoding thing in here. And so I get 3. Now we're down to here. Add register 3 to itself. Let's see, we get 4C and 4C. 12 and 12 is 24. That's 1, 8. 8 and 1 is 9. So I get 0098. Now, yeah, that's in register 3. Now I add that to itself and put it in register 4. 8 and 8 is 16. 10 and 9 is 19. That's 1 times 16 plus 3. Now I add register 4 to itself in register 4. 130 gives us 0260. Add that to register 3 back in here, plus 0260. 9 and 6 is 15. 02F8. Now I add what's in register 0 onto that. 8 and 3 is 11, that's a B. I give 02FB. I'm right where I need to be. Now we would do our unconditional branch back to here. When the thing is pressed, if we say that we get a carriage return in there this time, just to see what happens, we have that. We load that into there, we do the not, we add 1, and now we're going to add register 0, which is 0013. 13 and 3 is 16, that's 1 times 16 plus 0, 14, 15, 16, 1 times 16 plus 0. And so I get a 0 there. Now I will branch down to done, where I store the contents of register 3, 02FB. Let's see, we had a 0 in here, but that's replaced by 02FB. Okay, that's how input works. Aren't you glad the system does that for you? Now, just so things don't get too relaxed there, how would you change that if you were going to input this value in hex originally?
You would just add the numbers together, wouldn't you? Instead of multiplying it by 10, because you only need to multiply it by 10 to get the, oh no, you have to multiply by 16.
You'd have to multiply by 16. Okay, that's point number 1. But that's actually easier than multiplying by 10. I wouldn't have to use this additional intermediate register. Because to multiply by 16, I shift once, multiply by 2 to shift, do it again, that gives me 4, do it again, that gives me 8 times, do it once more, and I've got 16 times the number. So it's just 4 adds, and I don't need that intermediate register.
So you shifted over 4 places? That's the same
Yeah.
as multiplying by 16?
Yeah. That's actually the easy part. One of the things that makes this work so nicely is that 6, 7, 8, 9. If you look at the ASCII codes for these things, 3, 2, 3, 3, 3, 4, 3, 9. They come right in a row. Now, if you're going to input stuff in hex, you've got 5 more digits to work with, A, B, C, D, E, F. They do not come sequentially after this. To decode one of those letters into the actual digit value that you want to add onto the thing, you've got 2 different loops. If you look back here, we usually use uppercase, although if you want to allow upper or lowercase, then that's going to complicate it even further. A comes at 41. Fortunately, once you get there, they do come right together. It would really be nice if we could convince them to modify the ASCII code. There's a character that comes between these, ASCII code 40. It's this one. If that weren't there, it'd be cool. We could just maintain the same routine here. But you see, you're going to have to check on each digit to see if it's a numeric digit or a letter digit, because the thing you have to subtract is going to be different. Okay. The ASCII code is just a little bit of a fossil because it comes from way back. The code was developed for use with the teletype machines, automated telegraphy. There was no concept of using it for computers, for computational work, anything like that. And so the choices were arbitrary. I mean, they just stuck things in. Oh, yeah, we need this. Okay, let's put it here. It worked fine. It's just that those old teletypes were adapted in the relatively early years, and in the 60s and on into the 70s, teletypes were used as computer terminals because there were a lot of them around. They were cheap, they were easy to get, and so it's there. There was an effort to use a different code. Extended binary code for, no, decimal interchange convention.
It's much easier to remember.
I think that's the way it works out. EPSIDIC. This was developed by Big Blue. IBM, a lot of their computers in the 60s and into the 70s used terminals that used this particular coding, which was different. It's one of those bottom line kinds of historical things. They liked it because people that bought their computers had to buy their terminals, because their terminals talked EPSIDIC, and that's what the computers were expecting. Other companies said, oh, hey, look, we can sell more computers if they can use these old cheap teletypes that they've got around, so we set up the computers to use ASCII. Well, fortunately, EPSIDIC died. I was going to say one of the few bets, but I can list about 3 more that IBM missed. It has just disappeared, and now virtually everything works in ASCII. But it still has some of these fossil features to it, things that you have to look out for as you go through it. So actually, when you get down in here into stripping the ASCII code, you're going to have a branch in there. Check to see if it's a numeric digit, then you can do it this way. If it's a letter, you have to do it this way. One of those kinds of little problems that comes up. Okay. Questions about that? Can you see why we don't have you doing I/O on your first assembly language requirement assignment? It's kind of a semi-painful process. Now, let's see, output runs basically the same way. We will let's just take all of this off. Just like we have the keyboard status register at FE00 and the keyboard data register at FE02, we now have a display status register at FE04 and a display data register at FE06. Now, just like we had the problem, the reason we have to have this wait loop is because the computer can execute all of this and much more in the time between when you press one key and when you press the next one. No matter how fast you think you are, you're not that fast. And so you're going to end up with this waiting loop. Now, when we're going the other way, the same thing happens. That is, that the computer can push characters out there to be printed a whole lot faster than the display system can actually process them and get them out. And so the computer will kind of overrun the thing, and a lot of characters will get missed simply because there's not enough time allowed in there. So things work in very much the same way. This display status register, again, you have this most significant bit, which we can look at as being the actual status. Instead of calling it status, I'm going to call it ready. That bit indicates whether or not the display system itself is ready to accept the character to be printed. Okay, that's the way the thing works. The basic idea works like this. Here's the sequence. When the program puts a value into the display data register, the ready bit is cleared. That means it's set to 0. When the display finishes, I'll use the term posting, the character, the ready bit is set. By that we mean puts 1 in there. Okay, here's a, yeah, we can do this. I'll put a short name in here. Traditionally, we terminate character strings with a zero. A zero, not the character zero, in the case of the LC3, a whole word, not just a byte, but a whole word of zeros. So we put that in there. Okay, I'm going to put Bob in here. The B is 4-2, and the O is 4F. Okay, see if we can write here a quick routine to handle this. Let's see. Yeah, let's begin. I'm going to be working through this array, so I'm going to load the starting address of the character array into register 1. Okay, here's my loop. I will first of all, I'm going to load the display status register. Again, just like we did with the keyboard, it's an indirect, because what I actually store down here this is an FE04 and this one is FE06. Okay, I'm going to get that in there. And I'll wait. First time through, I'm probably not going to wait at all. The display's going to be ready for me. There's going to be a 0 in there. As we begin, since the thing is not busy, it's ready to receive things, so it gets a 1 in there, and I probably won't loop. After this one, I will. As soon as I come out of the loop, I'm going to print this first character. And I do it simply by saying store indirect. Oh, wait. I've got this system is a little harder to work with. I've got to load, well, okay. Load relative. Register 1. Okay, I'm using register 1 as an address, so I come down to here and load this thing into register 2. Now then, I can store that indirect register 2 display data register. It comes down to here, uses this as an address, that's the point of the indirect, and parse that thing out there into the data register. When I do that, it clears this ready bit, and it stays cleared until the character has actually been printed.
It does it right there at that line? STM
Basically, yeah.
clears the ready bit.
Yeah.
So that is storing the value that is in FE06 into R2.
No, store goes the other way.
Oh, excuse
You
me.
list the
It's
register
storing
first, but
R2
store always
into-
goes from the register to the memory.
Okay.
Load comes,
But it's from R2 to
It's a
FE
little
06.
confusing because these things look the same.
They do.
But remember that load is coming into here, store is going out.
So DDR is the target and R2 is the source.
I will increment my register one by one. And at this point, go back up here. Now, I've obviously got to change something.
What's an R1?
Because I come down here, what's in R1? The address of my array. And so by adding one, I go down so that the next time through the loop, I print this letter. Instead of printing this one over and over again, I go down to here, so on. Now, what I don't have in there is a way to terminate that loop. Okay, here's the nice thing about doing this. Zeros are easy to check for. They're a lot easier than checking for carriage return line feed or something like that. As soon as I load that character out of memory, I'll just say right here, for now, let's just say hope. And then I would finish down here with a dot end.
So we insert that BRZ done after the LDR?
After the load. As soon as you load that character out of your memory, check it, see if it's a zero. If it's a zero, that means you've come to the end of the string. If it's not, you print it. This is the actual print thing. When you store it out to that data register, that's the thing that actually does the printing. Then I adjust my address so that I'll get the next character in the string and go back and wait for the display to finish. As soon as the display finishes, I load the next character, which has been adjusted because I changed register 1 down here, so I really am at the next character.
But that's assuming that the next memory location is 0, right? But there's not already data.
It's assuming that there is a memory location 0 at the end of the string, yes. As long as it sees something, you know, the 4F or the 4.2, as long as it sees something that's not 0, it's going to keep pushing them out to the terminal to be printed. It'll quit when it sees a 0. But yes, writing it that way assumes that your character string ends with a 0 word. That, by the way, is not just an LC3 thing. That's a very common in virtually every assembly language around, that strings, character strings are terminated with a 0 character, a null character. Can't say 0 character because that's the character 0. It's what's called a null character.
There's a C string that works on the same concept, right?
Yes.
It finds the end of the
Exactly.
line.
Yeah.
The \0,
Yeah.
that says I don't mean the character 0, I mean the null string terminator, which is, in most cases, a byte of zeros. On this machine, it's a whole.
That's what we just learned in 1410.
The what?
That's what we just learned in 1410 about the null, the backslash.
That's what it is.
Did we?
That last,